At this point, I think I should introduce Robert. I'm not going to attempt to pronounce his last name because I know that I will get it wrong. Robert, now let me remember, is doing a Master of Science with a major in geospatial science. So it's great that we had a project that is geospatial in nature, but obviously interplanetary rather than Earth-based. And so he's been working on a project that's supervised by Anthony Legain and Gretchen Benedicts, titled A Tool for Visualising Planetary and All-Sky Astronomical Data. And this project has been supported by the Curtin Institute for Computation, so we thank them for their support of this project as well.
Okay. Hi again, everyone. As you know, my name is Robert, and it's a great pleasure for me today to present to you my project, which is about the development of tool for visualizing planetary data. So let's get started. As you know, imagery is one of the most important data sources, as it can provide the most current and the most important detailed information about an area of interest without actually going there. And currently, due to the advances in remote sensing, the image resolution has dramatically increased from kilometers to centimeters per pixel. So there are challenges in managing those data sets because they come from multiple sensors, they are high resolution, and they are large in volume too. And also, they require a long processing time. As such, traditional image processing becomes very inefficient, and a new tool is required to process fastly those images and then to visualize them smoothly to facilitate the analysis and interpretation in order to extract useful information. So now let's move on to the aims and objectives of this project. So the primary aim of this project is to develop a tool that can display high-resolution images efficiently and in a timely fashion. So the objectives are first to automate the physical mosaic of those tiles, then use display software such as Pano2 and KaiRPano to visualize those images in a flat view display on the web browser. And also, one of the objectives is to virtually mosaic some tiles of images and then visualize them smoothly with a spherical display cesium. Now, let's move on to the study area and data. So for this project, the study area is Mars, because Mars is the most similar and the closest to the Earth, and it is also the most studied planet after the Earth. In terms of data, we have used the context camera, or CTX, which is the best global imagery available for Mars until now. Last year, a machine learning algorithm have been applied to the whole CTX data to detect automatically the craters. That algorithm could detect the craters down to 50 meters in size. Why? Because craters are really important to determine the age of the surface of a planet. So this project is very important to examine the efficiency of that algorithm called CDA for subsequent analysis, which the team are going to use to visualize the detected craters with the imagery. Now, let's talk a bit about the CTX imagery. The CTX dataset covers almost 97% of the planet Mars. It is an 8-bit grayscale imagery with 5 meters resolution, and the imagery are available in 2 degree by 2 degree tiles from the global coverage of CTX Mosaic. And for the entire planet Mars, there is almost 15,000 tiles, which is equivalent to 5 terabytes of data. For this project, there are two tiles available. The first one is in format HIVE, which is directly downloadable from the NASA website. And the second one is the tiles already processed, and they are available in PNG format. So let's talk now about the methodology. We have used two methods to visualize the CTX data. The first one is to physically mosaic the PNG tiles, that is, they are already processed by the CDI or crater detection algorithm. And we have used a Python script to automatically stitch together some tiles. And then after that, we have used the display software, Pano2 and Carrier Pano, to tile the physical mosaic into small tile of 512 by 512 pixels, and then display in a flat view browser like this. And the second method concerns a virtual mosaicing. The virtual mosaicing is based on the use of the geospatial data abstraction library, which creates a virtual file in a XML data like this. It is an XML data that points to every raster, and then GDAL is used again to reproject and tile the virtual mosaic. And after that, the tiles have been ingested in a spherical view display like this. It is called cesium. So in terms of data processing, all the data has been processed with a desktop computer at the Space Science and Technology Center, which have 8 cores and 12 threads CPU, and the computer has 128 gigabytes of memory. And for the scripting, we have used Python 3.8 version with a Conda environment, with other libraries such as NumPy, OpenCV, and Pillow Image, apart from GDAL. Now, let's move on to the result. As you see in the table, this concerns a 6 by 6 tiles of image, and the first line concerns the mosaicing time with GDAL, not with GDAL, but with Python. And as you see here, the total time to prepare all the data before viewing is roughly 3 hours and 35 minutes for Pano2, and for Carrier Pano, it is 3 hours and 45 minutes. And in the first figure, it is a sample of display with Pano2 Pro, and this one is with Carrier Pano. As you see in the picture, Carrier Pano is a little bit better in terms of zoom in compared to Pano2. Now, this is the result of virtual mosaic. As you can see in the table, the virtual mosaicing is very, very quick, as it takes only 10 seconds for the same size of image. But for this one, the problem is the reprojection and the tiling, which takes almost 3 hours. So let's move on to the discussion. So for the tiles already processed, which are in PNG format, only the physical mosaicing is possible, because those tiles that don't have any spatial references. And the visualization with Pano2 and Carrier Pano is limited by the long processing time and the zooming. And also, the pre-processing time increases exponentially with the size of the mosaic. And it is also largely dependent on the performance of the machine used and the memory. But on the other hand, virtual mosaicing is very efficient, and it is much faster compared to the physical mosaicing. And also, we use in this virtual mosaicing the parallel processing approach, which makes the data processing much faster. And finally, with cesium, unlimited tiles can be ingested. So let's move on to the conclusion. So we have started to investigate the the visualization of physical mosaic tiles. They have already the craters on them. And then we visualize them with the display software Pano 2 and Kair Pano. We have seen high quality display despite some limitations such as the zoom in and the long time processing. And we can conclude that the virtual mosaicing is the best solution to visualize high resolution imagery because it is fast and it is also easy to update. And we have concluded also that cesium is the best display for high resolution imagery because it emulates better a planetary body. So for future work, a tool that can process automatically all the tiles of the planet mass can be a great idea to visualize all the entire data set. So before finishing, I'd like to thank the Curtin HIVE for funding this project, Anthony and Gretchen for my academic supervisor for their precious guidance throughout my internship. I'd like also to thank Wesley, my HIVE supervisor, for his technical support. And lastly, I'd like to thank Rakib, a HPC specialist at Curtin, for his assistance on data processing. So thank you so much for your attention, and feel free to ask if you have any questions.